Welcome everybody for our Physics and Astronomy colloquium titled Aerosol Transmission in a Time of COVID, presented by our own Alex Huffman from Chemistry and Biochemistry Department. Alex is a world-renowned scientist in aerosol research. He received his PhD from University of Colorado at Boulder in 2008, after which he moved to Germany in the prestigious Max Planck Institute as a postdoctoral researcher. He joined as a DU faculty in year 2011 as an assistant professor, and he received his tenure and promoted to associate professor in 2017. In this time, Alex has made numerous important contributions in the field of aerosol research, which is evidenced by his over 57 publications in peer-reviewed journals with a total citation of over 7,000. These are extremely impressive numbers. To further add to his credentials, he sits in the editorial board of prestigious journals in atmospheric research. He has also helped organize multiple conferences and special issue on bioaerosol research. From the very title of that, you can realize this is actually extremely important in the current topic and the context of COVID-19 being airborne. Alex is also one of those group of scientists who wrote an open letter detailing the importance of aerosol and aerosol dynamics in the spread of COVID. So I'm very happy to have Alex here and tell us and educate us about this extremely important topic, taking some time out of his busy schedule. So without any further delay, let's welcome Alex. Thank you, Alex, for agreeing to tell us about your important work.
Thanks, Kings, for that really nice introduction, and thanks, Barry, also for the invitation to give the seminar in the physics department today. I appreciate your invitation across the aisle and across the street to invite me into your physics seminar today from the chemistry department. I feel comfortable talking to physics people. I grew up as the son of a professor of physics at the University of Arizona. And so it's nice to be able to share some of the things I've been thinking about for the last few months that I think you'll find applicable to everybody listening. I will be talking today about how aerosols are transmitted in a room and specifically how those are related to the transmission of COVID. I've put here my email address and also my Twitter handle if you want to contact me later as well. So just as a brief intro into what we will be talking about, I'll give an introduction into aerosols in general, what they are, what it means, and then really spend time focusing those discussions on the type of aerosols that are transmitted in respiratory diseases. And I'll spend a little bit of time also talking about some of my opinions and some of the history on the development of the regulations in this with respect to the W.H.O and the C.D.C, and also spend a little bit of time thinking about some of the science behind preventative measures. And depending on how much time we have in the seminar, I will also talk about some of the things that we've been doing at DU to model aerosol transmission in classrooms and also look at monitoring ventilation through carbon dioxide and things like that. Just as a caveat, I'm an aerosol scientist. I'm not a virologist or a building engineer or a doctor of any kind. So we'll be talking about airborne aerosols and virus, but from the perspective of an aerosol scientist. And I'm certainly not meaning to give any kind of medical advice here. Just as a really brief statement, next week is the election. So if you haven't elected, go and do that. In Colorado, it's too late to mail your ballot, but you can drop it off. So make sure you've done that. Now, while I've been spending the last few months really thinking about COVID aerosols, the things that I've been doing for the last few years are applicable as well. And I'll just give one slide to give an overview of the type of things that we do in our lab. And I've broken this up on one slide into 4 general projects. The first of which in the upper left is the development of a pollen and mold spore counter. So the idea with these top 2 projects is to develop instrumentations that's small and cheap and deployable in ways that we can't easily deploy with the instrumentation that's available now at the cost that it is. So the idea is here, we take material pollen and mold spores and deposit it on a slide. We shine various lasers at those particles. We collect the light, and then you can see in the slide in the upper left, we see little strips of color. Those strips of color are fluorescence spectra, and we collect these fluorescent spectra, and then we can differentiate the species of the pollen and count them based on the spectroscopic properties. In the upper right, you see a cloud condensation nuclei counter. The idea is you see a fluffy white cloud in the sky. That liquid water has condensed onto a particle of some kind. And so it's advantageous to count the type of particle, the number of particles that cause these clouds to form. And so you can see if you squint in this black box in the upper right, rain falling inside this instrument. So we are literally counting the number of particles that have turned into rain droplets, and so we can make some inferences about what's going on. And so this is a project that originated actually in my father's lab at the University of Arizona. It's now is a collaboration with Handix Scientific in Northern Colorado to develop and characterize this instrument. In the lower left, it shows that we've spent a lot of time in the last few years taking instrumentation, especially laser-induced fluorescence instrumentation all over the world, looking at concentrations of biological particles, bioaerosols, and making determinations about different environmental effects that we see related to these biological particles. Also doing a lot of lab work as well. And in the lower right, finally, this is a bit of a departure from the other three. In this corner, I'm talking about the chemistry of certain reactions that take place on proteins that may be either in your body or in the atmosphere, for example, on the surface of pollen. And so there's a hypothesis that one of the reasons that we see increases in allergies in urban areas is some of the reactions that have been taking place in these pollen proteins. So if you have ozone and NO2, it can nitrate the proteins. And it's also been shown that certain nitrated proteins cause increases in allergies when they're taken up into the body. And so we are doing some chemical reactions in the lab and doing some development of these procedures, and also taking samples of pollen and reactions that are taking place in the atmosphere as well. So that's one quick slide of what we're doing in our lab. In the lower right, it shows a website that can take you to all the papers that we've been working on over the last few years. But for right now, we're going to spend our time talking about COVID-related aerosols. And as we transition into that, I thought that this was a prescient overview of some of the things that will come into play later in the talk. This is a special issue that I helped put together about a year ago, and this was the editorial preface for it. And I just took out a sentence from that, which is that key challenges in the study of bioaerosols, we'll talk about what aerosols are, but small things floating around in the atmosphere, biological being pollen, fungal spores, bacteria, viruses, things like this. So key challenges in the study of bioaerosol include the inherent multidisciplinarity of the work, and I underline that for a reason, often involving not only aerosol science, microbiology, atmospheric science, physics, chemistry, engineering, but knowledge of building science, ventilation, sampling, human dynamics, and so on, and countless other scientific disciplines. And so this is, I say this at this point in the talk, first of all, to say this is one of the reasons why I'm interested in the whole concept of aerosol science, because it's so intensely multidisciplinary. And also, this is the answer to some of the conundrums that we face with respect to COVID aerosols, because it requires a multidisciplinary, multi-teamed approach to looking at these things. Okay, so before I introduce the concept of aerosols any further, I want to say one of the things I've spent a lot of time with over the last 6 months is compiling resources related to the airborne spread of COVID. And so I have this Google spreadsheet that's openly available. So you can see the link here if you want to write it down. I've also recently learned how to make these QR codes. That QR code takes you directly to it. If you just want to take a picture of the screen, then you can go to this Google spreadsheet. And so it is focused on trying to educate people on the spread of COVID-related aerosols. There are multiple tabs, the first of which has a list of really high quality scientists that are active on Twitter, if that's something you're interested in following in more detailed way. And then this is just a really quick overview of all the tabs that are available, with hundreds of links that I've been compiling on a daily basis for the last few months. Reports and guides and hacks where you can learn a lot of detail on what people have put together in terms of how to go through, how to navigate the prevention and understand the spread of the disease. There's lots of media articles and summaries of infographics and educational videos. I've linked especially good threads, blogs, podcasts. There's a growing set of research science articles and also links to past live webinars and video recordings. So there's a treasure trove of information if you're interested in more aspects of aerosols related to COVID. Okay, so let's learn a little bit about aerosols and COVID. So first of all, aerosols themselves are small particles floating around in the air. So I put a few simple definitions here. A particle is simply some liquid or solid material that's small enough to stay suspended in the air for some period of time. Aerosol rigorously is that particle and the gas that's surrounding it. Aerosol really is the whole system, but we often call them aerosols instead of aerosol. And droplets are really just big particles. So the point at which it goes from a droplet to an aerosol, droplet is the big side, aerosol is the small side. This is where it gets a little tricky with the nomenclature, and more than just the nomenclature, as you'll get into. This common EPA summary slide here shows different sizes of particles: beach sand, 90 microns, human hairs, 50 to 70 microns. When we talk about aerosols, we're usually talking about relatively big aerosols are less than 10 micron. As they get into the fine mode, 2.5 microns and lower. But there's all sorts of different sizes. They come from everywhere. It's complex. We're not going to get into all the different sources of atmospheric aerosol. But to say that we think about this in two different ways, at least, one of which is the number concentration of the aerosols. And if you just lay out all the particles on the ground and count them, that's what we call a number count. And so on this x-axis here, this is a logarithmic scale of particle size. And so by number, the smallest ones overwhelm the biggest ones by number. But if you were then to accumulate or sum up the total volume associated with the big ones, it almost always dominates over the cumulative total of the volume associated with all those tiny ones. And so when we think about it, we often have to think, okay, do I care about the number of these things? Do I care about the sum total of the volume of these things? Or what property are we looking at? And so when we're talking about COVID aerosols, we're often thinking about the number concentration of these, but that will come into play a little bit. I should also say that as I go through this, I'm cognizant that this is a physics seminar, and so there will be a few places where I'll dig into a little bit of the physics and the math, but I also recognize that there may be some more general audience people here as well. And so if there are places that I dig in a little bit more deeply, don't freak out. We won't stay at that depth very long. We'll kind of come in and out. Okay, so from a COVID aerosol perspective, you have likely heard that just by me breathing out, and especially because I'm talking and relatively loud at that, I am expelling particles or aerosols, which I'll use interchangeably in this context. So this is a particle concentration. Notice that this is a log scale on both axes here. Particle size from 0.11 up to 100 and 1,000 microns. And so note that whether I'm speaking or coughing, I'm expelling particles. And this is some work by Lydia Moravsko's group in Brisbane, where they showed a number of times that when I'm speaking or coughing, it's more or less a bimodal distribution, where there's a mode that comes out at about 2 microns and another mode that comes out at about 200 microns. These shift around quite a bit, so don't get so worried about the specific peaks there. The point is to say that it's a really broad distribution. It does have some peaks in that distribution. Most of these are in the small micron mode, the small mode. 99% by number, and this, when speaking, only 1% of them are in this mode, because remember, this is a logarithmic axis here. Coughing, it shifts the distribution a little bit, but still most of them are in the small mode. So by speaking, I produce a huge amount of aerosol that are relatively small in size. Okay, so when we're talking about virus transmission routes, we have to think not just from the airborne side of things, but all the ways that we can transmit a virus. First of all, direct contact. I can have a virus on my skin, I touch you, you touch it, now it's on your skin. So that's what we call direct contact. Indirect is where that virus is on some other object, in this case a ball, and then that ball transfers to someone else. So when that virus is on something else and then it goes to you, it's called a fomite, but it's just indirect contact, but it's still touching. Large droplet spray is when, remember we just talked about there's a big mode of particles and a small mode of particles, which will, there's a continuum, but we're going to, for historical reasons, organize this into big and small. The big stuff we're going to call droplets. The small stuff we're going to call aerosols. The large droplets, for the most part, spray out and hit you in the face. We'll talk about this more in a second. And the smaller stuff goes into the room and floats around for a while. Now, historically, the dividing line between this has been 5 microns. And so from an epidemiological or a medical perspective, it has long been considered that this droplet mode only infects you at short range, less than 2 meters or so, 1 or 2 meters, because it falls down pretty quickly because they're big. Whereas aerosols, defined as anything less than 5 microns, will float around for a while. So we'll talk about this a little bit because the origin of that 5 micron cutoff is not supported by aerosol physics. And it looks like from the 1930s, but the route to get here is a little unclear. Somehow made its way into medical school textbooks, and that has become canon in terms of this, this difference. But there are some problems with what that introduces. Okay, so one of the reasons why this is important is because large droplets are sprayed from your mouth like little cannonballs, and they literally fly onto your face. Now, these are still much smaller than you can see. This is not spit flying in your face, although that would also have potential to infect you, of course. But large droplets, we're talking in the 100 or more microns in size, are too big to actually be inhaled. The physics of they have so much momentum, they can't traverse through your nasal passages around your throat, and so they slam basically into whatever surface they get to. So you can't inhale them. That's a really important point. And so it's essentially a form of contact transmission when you have this spray on your face. Whereas aerosols are small enough they can actually be inhaled deep into your respiratory system. And so this has a dramatic difference in the way that these particles are received and the way infection spreads. And so this also drives control strategies. Okay, so if they're in the room, you can put a filter in the room. If droplet spread is the dominant route, then filters in the room are going to do absolutely nothing. So various different engineering schemes will change the way you approach this, as does the infectious. It changes the infectious dose, and it can change the severity of the disease. So lots of different things stem from this difference in whether you think about this as a droplet spray, a ballistic mechanism, or whether it's an inhalable mechanism. That defines a lot of different things. And so, like I said, historically, that has been, the distinction between these two has been put at 5 microns. But as you'll see in the next couple minutes, that is not supportable by physics. And really, 100 micron cut makes a lot more sense. And it's been long known in the aerosol community that particles less than 100 micron are inhalable for the physics that we won't get into specifically, but like I said, the momentum allows it to traverse through your respiratory system. And so this was a recent article that Kim Prather from UCSD published in Science, just a short editorial piece, a 300-word thing. And I underlined one line here that says, to do so, we must clarify the terminology to distinguish between aerosols and droplets using a size threshold of 100 microns, not the historical 5 micron. This size more effectively separates the aerodynamic ability to be inhaled, and efficacy of interventions. And so the aerosol community is really pushing hard on this redefinition of aerosols to be considered up to 100 microns. And so I wasn't an author on this, but I helped edit it before it went to press. I should also say that I've noted here in the bottom that I had originally intended this to be a bit more of an informal discussion. Then I realized I had so much to tell that it sort of didn't happen that way, but I didn't have time to start from the ground up on every one of my slides at the beginning part of the talk. And so I have adapted some of them from some colleagues who have made their slides public. Okay, so from a close contact or a droplet, if you're in close contact with one another, droplets versus aerosols can make a big difference. Okay, so if you're standing right next to someone, droplets are spraying from your mouth and hitting someone's face, potentially. This is the origin of the 2-meter rule, or the 6-foot rule, to stay a little bit away. So you get out of this droplet spray. But you also have a plume of aerosol that's coming out of your mouth. And so that aerosol, if you are a long way away, can float in the air, as we'll see in a second, and you can inhale it. But if you're close enough, there's still a concentrated plume of these small particle aerosols that are near you. And so it has long been considered, again, in epidemiological and medical communities, that the droplet spray at short range really is the important one. We can ignore the aerosol stuff. This is an interesting study that on the y-axis shows the ratio of the large droplet spray to the short range aerosol spray and how important it is to exposure over a function of distance for both coughing and talking. So if you're talking to someone, it shows that anything, so the way you interpret this is anything less than 1 means that aerosols are the dominant exposure method. Anything over 1 means that droplets are more important in the spread of this. So this shows that you have to be talking to someone about 5 centimeters away from their face before droplets are more important to the cumulative exposure route than the aerosols are. So, and if you are talking 5 centimeters away from somebody else's face, then I don't think you're going to be too concerned about contracting COVID anyway in this. So the point is, at every point, droplets are minimally important from a physical perspective of spread compared to the aerosol route. Now, if you're coughing, it shifts it a little bit, but still you have to be within half a meter or so before the aerosols become less important than the droplets. Okay, continuing the theme of particle size, this is just for reference again, different particles. PM 2.5 is the fine mode that's inhalable. Influenza and SARS-CoV-2 and other viruses like this are about 0.1 microns in size. So you think, okay, these are really small particles, and so they're easily inhalable by themselves. But keep in mind that the virus does not fly around naked. It is embedded within a respiratory droplet. Now, as we saw before on the slide from Johnson and Lydia Moravska's group, these can be anywhere from a few tenths of microns up to hundreds of microns. So this is a huge distribution. Here it's just demonstrating as if the particle were half a micron in size. Even then, the virus is really small compared to the droplet. And then you can imagine if you were to increase the size of the particle up tenfold or 100-fold in diameter, it's obviously going to be small. So we could have potentially many virins inside. Now, this is important because you can't model the size of the virus. You have to model the size of the aerosol that it's transporting it. And the particle size defines all sorts of important things. How long it stays aloft, how far it can travel, how quickly it falls to surfaces, and then also where it deposits in the respiratory system, for some of the reasons I hinted at, how efficiently it's removed by masks and filters. It's really important to say that the physics of the particle is the same for all of the particles. Whether it's small or big, gravity and momentum and other physical forces are acting on it. Now they act differently as a function of their mass, but the physics don't magically change if it goes from small to big. And the way some of the definitions that the W.H.O has delineated these things, the only way you can get to that point is if you basically apply different physical forces to small particles and big particles, which is obviously physically impossible, but it is grounded in effectively a misinterpretation of some of the aerosol physics involved. And so, let me just skip that for time. Okay, so this is one of the important pieces to this puzzle, which is the settling velocity. How fast does the particle fall? So the y-axis here says how long does it take to fall? If I drop it from 1.5 meters, how long does it take to get to the ground? So if I drop a bowling ball, it's not going to take very long to get to the ground, right? So the diameter, if it's really big, it takes milliseconds, basically. It's going to hit very quickly. Now, as I get smaller, it stays up longer because the settling velocity is a function of the square of the diameter and the particle density and the viscosity of the air. So various different parameters here. But as we get smaller, it goes up as the square of the diameter. And so this curve goes up quickly. And so for a 10 micron particle, it stays up for several minutes. A 5 micron particle, which remember the WHO has long considered the definition between a droplet. So it would basically say if something is infinitesimally bigger than 5 microns, it's going to fall within 2 feet. Well, if it's suspended for 30 minutes, how is it going to fall within 2 feet? There's just no physical way that can be possible. And so a very simple understanding of settling velocity very quickly gets you past this 5 micron definition. So if you go up to 100, then it falls pretty quickly. Incidentally, I added this. So this is one of the slides that I took from Dr. Lindsay Moore at Virginia Tech. And so she prepared several slides. This one was exactly one of, I think, 6 slides that she gave to Dr. Fauci to try to convince him aerosols are important in this process. And so you'll see in a few minutes how that evolution has happened, and partially through this very slide. I have so we talked about the fact that particles will fall relatively quickly if they're very big, and that was assuming that there was the air was quiescent. There was no movement of the air. Now, air in the room, even you don't have to go outside where there's wind. Even in a room, there's movement of air. If there are people in a room, you have a body that's hot. It's causing convection, which causes wind currents. And so even at relatively small indoor air velocities of 5 centimeters a second, you look at different particle sizes, and you can see how far they can travel with even mild air velocity. And so a 5 micron droplet can go 100 meters at very low wind speed. So it's clearly not going to fall within 2 meters. Even a 10 micron particle is going to go 25 meters or so. And then if you model that at slightly higher indoor air velocities, but still reasonable, that same 5 micron particles can now go 400 meters. So now it's not going to go linearly through somebody's house for 400 meters, but this is just a 5 micron particle, and really even a 20 and 30 micron particle are going to mix pretty well through the room. Okay, so I'm going to skip these two, but just to say, I'll skip through really quickly because I have too many slides to talk about here. But the respiratory droplet is mostly water. When the water evaporates, it leaves some other stuff in the middle, proteins, salts and things like this. The virus is an infinitesimal amount of that. But that is a function of the humidity in the room. And so if you have really high humidity in the room, you basically don't evaporate anything. But if you have lower humidity in the room, like we do in Colorado, then that particle size will drop. And it actually evaporates really quickly within tenths of seconds or a couple seconds. So it doesn't take minutes for this evaporation process to take place. And so it drops pretty quickly. And so I chose not to show here that the particle that comes out gets even smaller when it evaporates, then it stays in the room even longer. So the size distribution shifts to smaller and smaller particles the longer you're there. There are also implications that I didn't have time to show here in terms of virus viability. In the last week, there was another article that came out that said the mid-range relative humidities is the best for virus deactivation. And so all of these things kind of wrap together as well. Okay, so then lastly, the resultant particle size, when it comes out, after it's been suspended in the air for a while, after it evaporates, will then try to deposit itself wherever it is. If it's big, it may land on something, including your face. The smaller it is, it has a chance to go deeper into your system. And so these blue colors here show that the bigger the particles, even in the several microns and above, deposit more so in the upper airway in the head because they can't make these bends around corners. The smaller it is, there's a mode in the few microns and then also smaller that deposits deeply in your lungs. That's important because instead of causing initiating infection in your nose, it can initiate infection in your lungs. And from a physiological perspective, that changes things. Okay. There's lots of evidence that I don't have time to go through all the evidence right now in terms of suggestions that aerosols are heavily to blame for many of the episodes that we're seeing with respect to COVID transfer. This is a famous one that you've likely seen in Guangzhou, China. This was one of the first that came out where one person was infected here, and then all these red circles are the other people that became infected. And it was postulated that it made more sense that the airstream was moving this around. There has been several studies in hospitals where an infected person was laying here, and then they measured the viable aerosol, SARS-CoV-2 aerosol, many meters away even though there was dividing curtains between them, suggesting that the only way it could possibly get over there would be through the aerosol phase. This one, and the Lednicki and Santarpia articles, especially. There's been hospital studies, there's been more animal studies that have shown this, and then also super spreading events have come into the news quite a bit. And so this is one example that was, again, one of the earlier ones, the Skagit Choir in Washington, where after a 2.5-hour rehearsal, there was one person asymptomatic that was sick, and 52 new people became infected because of that. And so thinking about these pathways, fomites, that's the indirect touch pathway, doesn't really make a lot of sense. The WHO and the C.D.C. also agree that that doesn't make sense in most cases. And in any case, he didn't touch, it claims he didn't touch any objects. Droplets, he wasn't that close to people. They were somewhat distanced. And during the break, he didn't talk to anybody, apparently. Going through a sequence of logic that I'm not going to spend much time on here, the droplet mechanism just doesn't make any sense. And really the only way you can possibly explain, and this and many other super spreading cases, is that the aerosols are spreading through the room. Okay, so with some of that in mind, this is a document, or not a document, but a infographic or a page from their website from March for the W.H.O, the World Health Organization, that says, it had this thing over here that says COVID-19 is confirmed as airborne and remains 8 hours in the air, and they put this big stamp over it that says incorrect. And basically they have fought tooth and nail against the idea that that COVID could be airborne, quote unquote airborne. And they said to protect yourself, keep at least 1 meter distance from others and disinfect areas you touch. So keeping that in mind, after everything I just said, how big of a particle does it have to be coming out of your mouth to land confidently before 1 meter distance? It's got to be hundreds of microns in size in quiescent air. It's just the physics of that are impossible to make possible. And so they have really dug their heels in on this. But it's not just then. This is the latest of their briefs from July 9th. It's some time ago, but they haven't updated themselves much since then. And so I'm not going to read through all of this, but it basically says respiratory droplet transmission can occur in close meters within 1 meter. They're still stuck on this 1 meter. They're not even up to 2 meters. They're literally on 1 meter distance. You're good as long as you're 1 meter away from everybody. And I think this is interesting. This just kind of says how they've dug in their heels. The physics of exhaled air and flow physics have generated hypotheses about possible mechanisms of SARS-CoV-2 transmission through aerosols. These theories suggest that a number, blah, 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 and it says, in theory, a susceptible person could inhale aerosols. However, we don't really see much evidence for it. It's basically saying, okay, but the evidence that you have for this is based on impossible physics, and there's no evidence for it, yet they want to suggest that direct transfer and fomites and droplet transfer of these big ballistic particles have to be spreading it. And aerosols couldn't possibly be to blame because basically because this 5 micron cutoff that they talk about, and everything bigger than 5 microns falls down quickly, and then we can walk away and ignore the situation. So the process of thinking is amazing. Okay, so a little bit on how we got here. And we're moving into some opinion areas here. This is moving away from the physics for just a couple slides here, but aerosols have never been important from the perspective of disease transfer. The infectious disease community has typically not really considered aerosols as a route, unless it's measles. They really like measles, and they have, and I didn't talk about this, but basically they define an infectious disease to be airborne if it has an R naught, the number of people you can infect on average, more than 10 or so, as measles does. They say, well, because COVID has an R naught of anywhere from 1 to several, and there are reports that say if you take the super spreaders into account, it's 20 or 15 or so in those cases. But anyway, since it's a small enough R naught, it can't possibly be airborne. It's like, okay, first of all, those are totally different thought processes. How infectious it is, and whether the particle can travel in air are two totally separate concepts that may or may not get convolved together, but that's not the issue. And so there is almost a total lack of people with, there is a total lack of people in the WHO with expertise in anything related to aerosol science. They're good people, they want to do the best thing, but they literally know nothing about aerosol science. This was, I thought, an interesting tweet that I had seen, and then Jose copied it here as well. Somebody who's worked with W.H.O in various capacities. I've yet to have a meeting or even an email with WHO groups that has included a single aerosol scientist. In fact, it's been 100% epidemiologists every time. They really need to bring in a wider group of experts. So really what this is saying is, and I've had conversations, I don't talk to the WHO directly, but a lot of my colleagues interface with them directly and say, it's really a group of epidemiologists. It's medical professionals who focus on the statistical transfer of disease, which is great. I have nothing against epidemiologists, but it's not the only way to look at the world. You also have to understand the physics of what is even possible, because if you say, our statistics suggest this thing, and then someone with knowledge of the physics comes in and says, yeah, but that's not physically possible, so let's come up with another theory. They say, no, that's what our medical school textbooks say. This shows why multidisciplinary communication is so critical. This, the C.D.C has been a little bit better than the W.H.O, and they're improving lately. This is just a slide on the slow evolution of their thought process that it's obviously too small to see here. From June 16th to September 18th, they made a big update and they said, this is thought to be, aerosols are thought to be the main way the virus spreads. And then 3 days later, they removed it from their website and basically said, sorry, that was a mistake. We didn't mean to say that. And everyone said, what? What is going on? Why did you do that? They eventually came back again on October 9th, and quietly, they didn't release a press statement or anything. They just sort of changed their website that did include some of the original wording. So they're evolving in their process. They're not yet to the point where they will take this new physical definition of 100 microns being inhalable, but they're at least making progress. But all of this confusion is really hurting the public confidence in how, who to trust. In an age where science is already distrusted, then you take the C.D.C and the W.H.O who have really made some missteps, and I'll talk more offline about some of the reasons I think that there is. But ultimately, one of the big parts of that is simply a lack of multidisciplinary. They think about things the way they think about things, and they're unwilling, in some cases, to then listen to someone outside of their scientific community to incorporate that knowledge in. And so that's what led to the development of this paper that was eventually published in early July. Interestingly, it was actually submitted to multiple journals ahead of time that was rejected multiple times before it made it to this point. And this is the semi-famous paper that came out that was signed by 239 scientists, and I was honored to be invited to sign it as well. And so the goal was really to increase awareness for airborne spread for kind of all the reasons I've been talking about. The need for masks, ventilation, and indoor air awareness. Because if everything is spread by droplets, you don't need to worry about ventilation. You don't need to worry about the time you spend indoors or filtration. All of that comes from an understanding that particles can be airborne for longer periods of time. And so this was really trying to push the WHO and the CDC, but especially the WHO, to really change their understanding of this. And in some people, you have your own private opinions on Anthony Fauci. Some people love him. Some people dislike him for various reasons. But I will say this, that he has really adopted a change in the way he looks at this. And so this is a quote from a talk that he gave. I think this was from this is from his Grand Rounds, Harvard Medical School Grand Rounds talk. There was some real misunderstanding about the respiratory droplets and so-called aerosolized particles. The aerosols and particle physicists that have approached this now have told us that we really have got it wrong over many years, and that particles greater than 5 microns still stay in the air much longer than we have thought when we used to say empirically that 5 micron drops to the ground. 5 microns might be aerosolized. We now know that's just not the case. Bottom line is there is much more aerosol than we thought. So I give him great credit for adopting new understanding of, that's exactly what we should do as scientists. When you see something that you now realize to be an error, data is brought to you, then you can adopt new thinking. I also think, just since this is a physics colloquium, the aerosol and particle physicists that have approached us. So who he's talking about is Don Milton, who's a doctor, Kim Prather, who's a chemist, Lindsay Marr, who is an engineer, and all of them think it's really funny that from Anthony Fauci's perspective, they're all aerosol physicists, so he can't differentiate. But anyway, so go physics. I'm going to skip through this, but just to say here, this conversation has huge implications, not just for this virus transmission, but for all respiratory virus transmission. If you have a wrong physical model for what's going on, it's not going to help mitigation efforts for any respiratory disease, whether it be another pandemic or whether it be respiratory seasonal flu. So it really needs to update. And I'm cautiously optimistic that all the effort that the community is putting together is really pushing the envelope and updating a physical understanding of these disease transmissions. Okay, so what does this mean for you? First of all, I think one of the best analogies to this is smoke. Smoke is an aerosol. It's little particles with gas floating around it, going around the room. It's relatively small in size. If you see smoke building up or traveling around indoors, respiratory virus can do the same thing. It's harder to see. Smoke, for various reasons, is visible. Think of a smoking section in a restaurant from the 1970s or 1980s. I mean, just because someone's smoking on that side doesn't mean you can't smell it over there. It can travel through air. Same thing with COVID aerosols. Don't get too hung up on the smell part of the analogy. I recognize that your olfactory sensors are pretty sensitive to smoke smell, and so you can smell things at really low concentrations. That doesn't mean it would be you'd be infected at that point. But anyway, some epidemiologists really hate this analogy because it breaks down at some point, as all analogies do. Okay, you know you need a mask. I'm not going to belabor that point at this point. I think everybody knows this is when it compared to earlier science papers this year. Just saying, it makes a big difference both for breathing in and breathing out. The fit of that mask is really, really important. And so this is some visualizations by a group in Delft in the Netherlands, where they showed some kind of aerosol, and they used some cool light to basically show, in this case, the aerosol wasn't going through, it was basically just being blown back behind them. You may see a lot of times people will do a test where they'll try to blow out a candle or something with a mask on. In some cases, that can be fine. It just depends. It's a little bit more complicated than just that, because it can either mean the mask is making the air coming out in a diffuse way, so it doesn't come out in a concentrated jet to blow out the candle, or it could mean that the resistance to your airflow is so much that it's just blowing out the back of the mask. And so if air is flowing out the back of your mask, the aerosol is doing the same thing. And so Jose Jimenez likes to say, don't stand behind somebody wearing a mask, because if it's poorly fitting and it's too resistive, basically all you're doing is blowing all the aerosol right behind you. So the point is, it needs to be well fitted, and it needs to have a low enough resistance that your air goes through it, but then it filters out the particles. How loud you talk is a big deal as well. It makes sense that if my voice talking is expelling particles, then the louder I talk, the more the velocity, the farther it goes, the more aerosol that comes out. And so this shows, as a function of volume, what is the transmission probability at different air exchange rates in a room. Don't worry so much about that, but to say, as you talk louder, the probability of transmission goes up. So this is one reason why bars and concerts are potentially dangerous, because if you have a lot of loud voice, if the music is loud and for people to talk, they have to really scream, they're shoving out huge amounts of aerosol. And so this is also why singing can be dangerous as well. In the category of what can you do about it, one really simple hack is to, if you're in an environment where you need to clean out the air for whatever reason, you have a mixed company of some kind and you want to make sure the air is a little cleaner than it is, Instead of buying an expensive air cleaner, one simple thing you can do is to buy a box fan for $20, attach a $20 MERV 13 filter to it, a furnace filter that you can, they're largely sold out right now, but because a lot of people are doing this, but literally tape them together and you have a pretty high efficiency air filter for about 40 bucks. It's effective not just on COVID aerosol, but also wildfire smoke. So I did some tests in my basement this summer when the wildfire smoke was high, and just focus on the black line here. That's the particle counts, because you can see that the particle counts are rising. And then at this point in the green, I turned on the fan filter and it just took a lot of the particles away. Again, I opened the window, smoke came in, closed the window, turned the fan on, and it took them out. And so in this case, this is kind of a best case scenario, but it took out something on the order of 98% of the particles in the room. So just to say, the stuff that we can't see, there are ways to take it out through filtration. And this is kind of a summary slide of what you can do. You may have seen the Swiss cheese model that's been around for decades from different perspectives, but several people have put this together from a COVID response perspective. And he's gone through all sorts of iterations, and I'm glad that he took some of our suggestions to break this up into different things. But basically the idea is a layered approach is important. There's no one silver bullet to any of this. First of all, you want to try to control it at the source. Wearing masks, staying home, just staying away from people. Obviously hand hygiene, avoid touching your face, and limit the time you spend in crowds or indoors. And then there's a set of shared responsibilities that goes into vaccines and quarantine isolation. So anyway, all of this together, the various layers help us as a society together. See if you can also find Misinformation Mouse, who's eating away at the layers that he added in the last layer. Okay, so all of that was what it means to COVID and aerosols. And I don't have a whole lot of time left, but I want to share with you some of the things that we've been doing at DU, that I've been doing at DU to help try to lower the risk that we face. Okay, so one of the things I did was some modeling, aerosol modeling. So this is based on a relatively simple box model, the Wells-Riley model that was published first in 1978. It simplifies the probability of airborne infection. Basically, it assumes the room is well mixed, and that as soon as you breathe it out, it's immediately mixed into the room, which is a bad assumption, but it makes the math pretty easy, and it gives us the ability to do some stuff. Coming into play in several places is going to be the term viral quantum or quanta. That just means how much, it's related to the probability of you getting infected. One quantum is a dose of virus required to cause infection in 63% of the people. Okay, so basically one dose has a chance of infecting you. If you have 2 quanta, then it's 1 minus e to the 2, and your chances go up a little bit. And so we're going to track the number of quanta of this. We don't need to know the number of virins, the number of actual virus, because that's more complicated than we need to know. We just need to know the probability of getting infected, which we can use here. And so this has been around for a long time, but Jose Jimenez, who's actually my former PhD advisor, put this together into Google spreadsheet, and there's a link here if you're interested in this, and all of the links of everything I've shown are also in that spreadsheet as well. That was picked up by all sorts of other people, including National Geographic, who put a pretty cool web interface together, so you can click around and change variables and just slider bars, and it'll predict your aerosol risk. There's been several of these. They're all freely available. Some are a little easier to use, some are a little more complicated. And so basically the gist of that is that you put in some assumptions, the room volume, the number of people, the ventilation rate, the filtration, and the time, some of which you may know, some of which you have to guess. The spreadsheet version of this helps you by suggesting some numbers for a few of these things. If you use the National Geographic, it doesn't matter, you can play around with it otherwise. And then it outputs the probability of infection, assuming some community infection probability, or assuming there's a super spreader in the room. So I took this and wanted to do more with it. So I rewrote it into a program called Wavemetrics Igor Pro so that I could output all sorts of it with individual button clicks. So this is just a screenshot of the panel that I put together where I click a bunch of stuff and then I click a button and then it spits stuff out. If for whatever reason you are interested in this and you do Igor, let me know and I can talk to you about it. Okay, so since it's a physics seminar, let me say just real briefly a few of the things here. And I'm going to go through quickly because I know I don't have a whole lot of time left. So it's a box model. That just means we put it into a box and assume everything stays in the box, or we have loss mechanism. Okay, so you emit, you're talking, the aerosol goes into the box. You also get it out of the box by removal mechanisms, ventilation, filtration, virus decay, gravity, some of the things we've talked about. We sum those up into a net removal. And so then we can adjust the emission as a function of several different things, the number of infected people and how many people are wearing masks. We can adjust it a little bit. This is the part I added to the model that assumes a non-zero beginning point, that there's some concentration at the beginning. Don't worry too much about the math here, especially with the time we'll have. But we can add, we can get a concentration of quanta in the room. We integrate that numerically and add in this term for how much there was before, and we get some term that we can add up that basically says the emission rate of exhalation, the number of infected people in the room, some mask properties, and the wait time and the duration of spending time in the room. And we can then do some more math and get a number of the number of quanta that you have inhaled over that period of time, which is important because that relates to the probability by this relationship. So for any individual class, I use the model to predict the probability of infection based on all these assumptions, or also over the course of a quarter. So we can get these outputs to say, okay, how likely are we to be infected based on this simple model? So then I ran it through all sorts of times. And basically, this is just saying it was just indoor air. I wasn't thinking about the other side. But it's also meant to be approximate. I'm not trying to get 10% differences here. It's orders of magnitude that we're trying to get at. And we were using this to make some decisions about the fall. Put in a whole bunch of numerical assumptions. We don't need to work through what they were. But anyway, I assumed a variety of values. And so this is one of the types of outputs we can get here. On the top, it's assuming that everybody in the room has the same probability of being asymptomatic spreader based on whatever the community probability of infection is. The bottom shows the what happens if you have somebody in the room that's an asymptomatic super spreader that spreads up to 10 times or more as much aerosol. And then these output axes here, the left is the probability of any individual person being infected. And then we can accumulate that into the total number of COVID cases that would be expected in that classroom over the course of the quarter. So basically, without thinking about the specific details here, we see relationships based on what assumptions we're making and how many people we would expect to get sick in these situations. But after I put the model together, there's all sorts of ways we can think about this. So I inputted by changing the number of students in the class, the wait time after class, the air exchange rate, the additional filtration units, the community probability, the relative infection rates, and the duration of class. Basically, I varied all these different parameters to see what happens. And you can see some relationships here we don't have time to look into, but I'll summarize by saying we then looked at the probability of anybody infected as a function of different classrooms in activities that we expected in those classrooms. And I focused this on music activities because you're emitting a lot of particles during those activities. And it's potentially riskier, like the Skagit Choir super spreading episode. And so I looked at that as a function of wait time between classes, the different bars here for different classrooms, and also as a function of class duration. You can see that there's a more or less linear relationship between increasing the duration of the class and the probability of you getting infected. So we decided that by moving rehearsal times from 45 minutes to 30 minutes, then we would decrease the risk by some different amounts based on which classroom we were in. I also looked at, well, what happens if we added extra filtration units? Would that help? Well, in some cases, yes. You have a pretty big reduction in the overall probability by adding 1, 2, or 3 filtration units. But in some cases, there's already so much ventilation in the room, it doesn't really matter if you add a little bit of extra. It's not going to make a difference to the already fast ventilation rate. And so we use this to think about, okay, where could we put some ventilation? Where could we put some filtration units to make a difference? Also thought about practice rooms, but we'll skip that. And so all of that to say, this got wrapped up into the protocols that the provost office wrote for the music school, basically setting the ensemble times for the how long the classes would be and how long the wait time, which made a big difference based on the model. 12-foot distancings, various different things. So we made some, use this model to make some real decisions to make everybody safe. But because we're all humans, we may or may not follow through with that. Okay, so it is 4:57, so I'm going to mostly skip through this. But just to say, we're also deploying CO2 sensors in a variety of classrooms on campus, because in a room, you have people breathing, you breathe out CO2. The only sources of CO2 in the room are you breathing or some flame combustion. As long as you don't have flame in the room, you're the only source of CO2. And so we can use that as a, so you're breathing out CO2, you're also breathing out aerosol. So CO2 can be a rough proxy for the aerosol that's potentially infectious. And so I got my kids to help with some experiments, and we won't talk about this. You can measure the air exchange rate in a room based on, it basically follows first order kinetics. You plot the natural log of the concentration, and the slope of the line is the air exchange rate in the room. And so based on my model, the probability as a function of the CO2, there's some relationship that varies based on the numerical assumptions. And so using that, we thought, okay, well, let's put some CO2 sensors around campus. And so we put 12 of them around campus, focusing on high-risk activities, the Newman Center, Coors Fitness Center, and a couple classrooms. So they're currently reading every 2 minutes in 12 classrooms around campus. And so this is the Coors Center. This line at 800, so this axis here, CO2 concentration, is a function of time. The weight room, the cardio room, and the pool deck. So this line is 800 parts per million. Outside, it's 400 parts per million. The higher it gets, the worse the risk. But we arbitrarily draw a line at 800 to say, if it's there, that's doing okay. So Coors Center is actually doing fairly well. Most of the time, Newman Center and most rooms are doing okay as well. This dashed line, again, is 800. These are 3 different ensemble rooms. But notice there's there are times that the concentration in some of the practice rooms goes way above. And so this is the last little brief story that I'll show here, because I think it's fun. CO2 concentration is a function of time. This was 2 different rooms, a jazz ensemble room and a vocal practice room. So notice that this line is 800. So the concentration was going above 800 at some points. But I noticed, I drew these green lines that the concentration of CO2 dropped very sharply at 5:30 every morning. But then in this blue bar, I noticed, that's the weekend. It's not happening on the weekend. It's not dropping. And I emailed facilities and said, you're turning off the ventilation at 6 p.m. every night, and you're turning on at 5:30 in the morning, and you're not leaving it on the weekend. And they said, you're absolutely right. We are. We should change that. And so now they notice these big peaks here. This is before they changed the ventilation. Now, it's on starting at 5:30 to midnight instead of 5:30 to 6 p.m. and it's on the weekends. And now you don't see these big peaks anymore. So we've reduced the CO2 concentration and therefore the aerosol risk in Newman by looking at the simple CO2 sensing. And if you're interested in more, one of the links is Jose has put together is this FAQ that is tremendously useful if you want to look for this. It answers every possible question you can think of with respect to airborne aerosol. And just a simple plug for Science Twitter. I am new to Twitter, but I have been tremendously impressed with how much I have learned on a daily basis through Twitter. And so I used to think it was just for, I don't know what I thought it was for, but it's actually really useful. Okay, and so this is my last slide, so thanks. Just to say, the cases in Denver are skyrocketing. That's not good. This is serious business. We got to still pay attention. This is one of the infographics that's, I don't know that I love the acronym, but it's a civic duty, basically. Think about all these different things. But the point is, remind somebody else to take this seriously. If you're interested in getting more updates, go to this website. This is where all of those resources are. And then if you want even more frequent updates, join Twitter and follow people along. So, okay. Thanks for bearing with me as I went a little late and as I spoke a million miles a minute. And with that, if anybody is still awake, I will be happy to take some questions.
So he's a mess.
And I can stick around if even at whatever point people have to leave, I can still answer some questions.
Yeah, I think
Debbie's got her hand up.
okay, go ahead, Debbie.
Hi. So one of the things, really good talk, Alex. Thank you so much. I learned a lot. One of the things that you talked about was how humidity plays a role. And it seemed like there were competing factors. So you talked about how with low humidity, the droplets are smaller, so they'll travel further. But with higher humidity, the viscosity of the air is higher. So that decreases the settling velocity. So I was just curious what, when those factors are competing, if one plays a larger role than another.
Yeah, it's a good point. So a couple different responses to that. And it's actually even more complicated than the things that you just alluded to, because there is, how does the humidity change the dynamics of the aerosol itself? How does the humidity change the dynamics of the ventilation system, as I've been called out about recently, because I don't know that much about ventilation system, because the that can change the way that the HVAC system operates. And there's also how the humidity affects the likelihood of infectivity once it gets into your body, which are all totally different like scientific disciplines. From an aerosol perspective, the settling velocity, it goes by the square of the diameter and only to the first power of the viscosity. So the diameter wins in that case. And so the fact that it's dropping in size keeps it in the air longer. And so in that sense, the lower the humidity, the worse that it keeps it up in the air. But the viability of the virus, there's been several different studies that have showed that, and I don't actually know mechanistically from a virus perspective why this is, but high humidity is bad for this virus, low humidity is bad, but an intermediate virus, humidity helps kill the virus, inactivate the virus. And so all these things, I'll say this as a long-winded answer to a short question. Lindsay Marr, who's one of my go-to people on these things, she's one of the best viral aerosol people in the world. She has been pushing this effort to recommend keeping humidity between 40 and 60% in the winter, because there's kind of a happy ground that kind of keeps these things. The epidemiologists don't like that because they think that humidity should be as high as possible because your body works better at higher humidity. But from an aerosol perspective, a mid-range is better.
Thank you so much.
Yep.
Bob Stencil.
Right. Thanks, Alex. Good talk. The question is about aerosol shape, particle shape, because it could affect the buoyancy and the fall time in air. One could imagine that the static forces in liquids would draw these things into spheres, but do deviations from spheres much matter, or in the big ensembles you're talking about, is spherical approximation just fine to first order?
The simple answer is spherical approximation is fine for a couple of reasons. One of which is if it's not a sphere, the physics involved get crazy pretty quickly and it's almost impossible to deal with. Second of all, from a respiratory aerosol perspective, they're almost totally liquid, and so they're little water droplets, so they're pretty spherical. And so once they dry out, they may be more amorphous, but then it gets complicated. But absolutely, particle shape comes into play all the time in aerosol science, and we deal with this. But trying to predict the shape and the dynamics is virtually impossible.
Right. Could you put back up Lindsay Marr's Twitter address? I would like to catch that.
It's It's Lindsay Marr. It's at Lindsay Marr. Did I have, oh yeah, it's, let's just go to, let's say slides. There we go.
No D in the Lindsay. Got it. Thanks.
Yeah, correct. Yeah. So yeah, she is an excellent person to follow. As there are several. If you are interested, or if you just want to not join but click around, I can share a small handful of people that are really
There is a question on temperature effect. Can you comment on that, Alex?
Complicated. Temperature affects things in lots of different ways. I mean, temperature of the body causes mixing in the room, and so that causes lofting, and so that changes the turbulence in the room. It changes the virus viability. Like I said, that's not so much my area of expertise. It changes the evaporation patterns in the room. If the air is hot, then it evaporates faster. So yeah, it comes into play. If you have a more specific question, I can see if I can answer it or not.
Barry, you had a question?
Yeah, I do have kind of, this is a little bit random, but do you have, in your lab, do you have a method for producing aerosols, like a water droplets that you could study?
Yeah, so we have, there's various different ways we can make droplets. The simplest is
Is it a humidifier? Oh,
literally,
a squeezy bottle.
Well, yeah, not the simplest. The simplest is lighting a match. But this is just a medical nebulizer. If you have asthma and you have to take a breathing treatment, as I did when I was a kid, you basically put the albuterol in here and then stick it in your mouth and you breathe it. And so we have a couple different contraptions that basically nebulize water like this, and we just put solutes in there, and it aerosolizes it. We send it through a silica gel drying tube, and it basically evaporates the water off really fast, and then we're left with whatever solute was left. Or if we want to deal with a droplet, then we can do our stuff on it.
Okay, I need to talk to you. Yeah.
There's ways to aerosolize it from dry powder or from liquid, or there's sonicating. There's all sorts of different ways to aerosolize things.
Cool. I'll drop you an email. We can talk about that. Okay. I'm going to try to come steal some of your stuff, I think.
All right. What else? I see some chats coming, but I haven't looked at them.
Kings and Alex, I have a question, please. Yep. Matthew here. How are you?
Hey, good.
Good. Alex, could you please say something, or perhaps it's not even worthwhile, about UV, please, on droplets and perhaps the virus? I know the virus is out of your area, but
yeah. Well, so there's so it's outside of my area, but I know enough people that work on this. So UV is, there's been some studies, certainly on many different viruses, but also now on this virus, that shows that UV pretty well inactivates the virus, depending on the wavelength. UV in the room is, you don't want to do that because then you irradiate everybody in the room. And so that has significant negative consequences. And so the main way that you would want to, there's two ways. One is if you buy a fancy HEPA filtration unit, some of them have germicidal UV lights in the back of them, basically, that kill. It's fine, but it's almost an unnecessary add-on, because as long as you have a filter, as long as the particles get taken out of the air, you don't really care whether they're alive or dead when they hit the filter, because they're not coming off the filter again. But where they especially come into play is what's called in the upper air, the upper room, germicidal UV, where you basically have UV lights in the air ducts that basically irradiate everything that's coming through it. And that can work really, really well. So that's not my area. Shelley Miller at CU Boulder is one of the experts in that area. Is that where you were going with that question?
Yeah, that's exactly. Thank you. Thanks, okay. Alex. And also, yeah, I suppose being outside.
Yeah, exactly. So that's one of many reasons why being outside is much safer than indoor. The most important of which, and I didn't talk about that here, is just aerosol concentration. It builds up in a room. You go outside, you have huge ventilation compared to what you do even in a well-ventilated indoor space, and it just blows the air away. And so that doesn't mean you can't transmit the virus through airborne pathways outside, but the relative probability is dramatically less. There's at least a factor of 20 is the modeled probability that I've seen, but that's if there's very little wind. If there's more wind, it's like way more than that.
So as an aerosol scientist, is it clear to you what's driving the current increase in the cases in Denver and maybe worldwide? I think it seems to me there's a simple answer to that question, but I'm going to ask you. Well, not necessarily. It's a broad question. I just want to see what he.
So from my perspective as an aerosol scientist, we all have our perspectives. My perspective as an aerosol scientist is that there is pretty good consensus coalescing in anyone that I know of that knows anything about aerosol science, that aerosols are the driver of this. To say that not any one of these, in fact, what's on the screen is a good piece of this. None of these are the silver bullet. All of these come into play. It's a question of what do we do about stopping it? Where do I put our most energy? So yes, you can transfer it from your hands. But if we focus so much on hand hygiene and we forget about the air hygiene, then we risk bad things. And if you do the other, the chance, it looks like the chances that the touch-driven transmission driving this is very, very low. It's unlikely that that's a big part of it. So it's a lot of the models that I've seen suggest that it's 3/4 aerosol and a small amount of some of the other stuff, basically. So I really think it's people not wearing masks, people being indoors when they are not being careful. So I didn't come back to this, but really the answer is simple. As an individual and as a community, wear your mask, stay at indoor spaces when you can. And if you can't, limit the time you spend there, still be socially distant. And the next layer, if possible, if you're in a place that it's not great, add a box fan. Like my background is hiding it, but box fan or open the windows, things like that. So the things we need to do are not hard, but we do need to do them.
Okay.
So I would say, I mean, if you're going to have restaurants where people are inside and take off their masks to eat or drink, do we need to require all restaurants to have box fans and MERV filters at every 6 feet or something? I mean, would that help?
6 feet, but yeah, I mean, a lot of my colleagues are pushing hard for if we're going to have restaurants open. I mean, it really depends on the community positivity rate. If it's relatively low, we can deal with it. But as it's going skyrocketing, like it is right now, going
Almost
inside
everywhere.
a restaurant is just super risky. I mean, I am not going inside a restaurant. I haven't been since March, but I'm definitely not going inside a restaurant right now. But if you are, then yeah, we just need to crank some ventilation, add extra filtration. A lot of people I know are really pushing for having CO2 sensors as standard. One guy, Charles Haas, distinguished professor from Drexel, said, we have smoke alarms, like this invisible one that I'm showing the screen right here.
Yeah.
That are everywhere. They're just standard practice. This helps protect us against fires. And we have carbon monoxide sensors. In fact, this one has one in it. But we don't think about CO2, which is a good proxy for the relative level of the indoor air quality, both with respect to respiratory aerosols, but all sorts of other stuff as well. If we just put this in standard practice into buildings when we built them, we would have a measure of indoor air quality. We have thought, I mean, I didn't have time to talk about this, but it's really fascinating. If you get into the history of, we as a society are so focused on touch that, because it's easy to see, I can visualize that my hand is dirty. It's hard to visualize that the air could be clean. And so we're really very far behind in terms of cleaning air with respect to both air pollution and respiratory viruses. So, I mean, I could keep going on this stuff for hours, but those are some of the things I would say.
That's okay. Thanks, Alex. Just thank you for the talk and thank you for all the hard work you're doing. I mean, you're such a benefit to our community and everything you're doing with the aerosol community. It's just, thank you, rockstar scientist.
Yeah, thank you.
Yeah, thank you, Alex. I had a quick question on the fan. So I saw it went down and then it went back up again, but in
Because I opened the window.
Oh, okay, I see.
Yeah.
But the idea is just keep running,
It
right?
would have stayed down for a long time, but it was just uninteresting. So I opened the window.
And how quickly it drops?
Well, it depends on the air ventil. It depends on the volume of the room. But the fan pulls a couple hundred cubic feet per minute. And so It can exchange the air in the room after, it just depends on the size of the room. My basement, it took like 10 minutes to go down by like 90% or something like that. So, and it's reasonably sized basement. So these things would actually push a lot of air. They can be really useful. In fact, I made a set of these for, so my older kids are staying at home for school. My youngest is going to preschool. So I made a set of these for every room in my daughter's preschool. If that says anything to you.
Very good. Okay, let's thank Alex again for really educating us. Thank you so much, Alex.
Yeah, you're welcome. And like I said, if anybody has any follow-up questions, feel free to send me an email, find me on Twitter.